Okay, so we're going to be doing some guided practice for all three of the ramps problems. I'm not going to be plugging in numbers, just going to be talking about how you're going to be finding your numbers so that we can jam on through the entire thing in one video. So first thing, we got a 5 kilogram block sliding down a 35-degree frictionless ramp. So we've got mass and we've got our angle of 35. Okay, so we're drawing a vector diagram. We got a ramp, and this one specifically was looking at a frictionless ramp. So we've got our block, and there's only going to be two real forces acting on it. You're going to have your weight pointing straight down. You're going to be having your normal force pointing off perpendicular from the ramp. Okay, so it told us we had a 35-degree angle, so we got 35 degrees right there. And then it's asking us to also draw our components of our weight. So that is the side of this weight that is going down parallel to the ramp. I'm using a dotted line because it's not a real force, it's just breaking up our weight into pieces. And we've got the force pointed into the ramp that is canceling out our normal force, and that is our perpendicular component. Okay? And that, we also need the angle between the weight vector and the perpendicular component, so that is, whoop, right there. And that theta is equal to 35. These two triangles have similar dimensions. Okay? So B, determine the weight of the block. When you're looking for weight, it's just mass times gravity. So plugging and chugging. Perpendicular component. Whenever you're looking for the perpendicular component, that is this adjacent side on this triangle over here. And your weight is the hypotenuse, so adjacent and hypotenuse, that means we're looking at cosine. Okay, so that perpendicular component is just going to be your weight times the cosine of the angle. All right, that angle being the same as the angle of the ramp. Okay, parallel component, that is the opposite side on that triangle. So instead of cosine, you're going to be using sine. So weight times the sine of your angle. Okay. C, determine the acceleration of the block down the ramp. Now when you're looking at a frictionless ramp, only one force goes uncanceled. If we're looking at this, your normal force and your perpendicular component cancel out. So all that's left is your parallel component. All right. And when you're looking at the acceleration is just your net force divided by your mass. In this case, because we've only got one force acting on this thing that doesn't get canceled out, that means it's just going to be F parallel divided by M. All right, if we look at F parallel, it's your weight times the sine of your angle. Weight is mass times gravity, which means you can cancel some out. And when you're looking at a frictionless ramp, your acceleration is just going to be gravity times the sine of your angle. Okay? You can only use that for frictionless ramps. All right, so now the final speed of the block as it reaches the bottom of the ramp, which is 8 meters long. Okay, so we're looking for final speed. We've got acceleration. So acceleration is whatever we had there. We've got a distance of 8 meters. This thing is starting from rest, so you've got an initial speed of 0. So with acceleration, initial speed, distance, final speed, that means we're looking at formula C. So you got this VF squared equals VI squared plus 2AX. Okay, looking for VF there, you're just gonna have to get that squared off. So take the square root of the other side. So square root of your initial speed squared, so that's 0, plus 2AX. Okay, acceleration, what you found in part I, and then X being the 8 meters it was traveling. And we're done with number 1. Looking at number 2, we got a 5 kilogram block starting from rest, sliding down a frictionless ramp, which is 4 meters long along the ramp and 2 meters high. Length of the ramp is the hypotenuse of the triangle, and the height of the ramp is the opposite side of the triangle. Okay, so we're looking for a free body diagram of the forces on the block. We're going to have the exact same ones we had before. You got your weight pointing down, you've got your perpendicular pointing into the ramp, you got your parallel pointing down the ramp, and you've got your normal force pointing up, perpendicular from the ramp. Okay? B, the angle of the ramp. Now it told us that this thing was 4 meters long, so that's your hypotenuse, and 2 meters high, so that is our opposite side if we're looking for that angle there. So we've got hypotenuse and opposite, so you're going to be using your sine. So sine theta equals opposite over hypotenuse. We're looking for that angle, so that means taking the inverse sine of that opposite side divided by your hypotenuse. So inverse sine of 2 over 4. Do make sure that your calculator is in degrees. If you get a weird number, you're probably in radians. C, determine the component of the block's weight that is perpendicular to the ramp. So you're looking for the perpendicular component, so just like before, that is going to be FW cosine theta. Anytime you're looking for the perpendicular component, FW cosine theta. Normal force on the block. So if you're looking at this block, it's not moving up off the ramp, it's not moving down into the ramp, which means that these two forces have to cancel out, your Fn and your F perpendicular. So that means that your normal force is just going to be equal to the force that you just found, because it has to cancel it out. It's just in the opposite direction. Part E, determine the component of the block's weight that is parallel to the ramp. All right, so looking for the parallel component, F parallel is just that opposite side, so that's going to be FW sine theta. Okay, F. Determine the block's acceleration, just like before. If we're looking at a frictionless ramp, A is equal to G sine theta. So gravity times the sine of your angle, in this case the angle being whatever you found in part B. Determine the block's final speed when it reaches the bottom of the ramp. Okay, so when we're looking at this one, the information that we've got, you've got initial speed, you've got acceleration, you're looking for final speed, and we also know distance, the distance that has traveled down the ramp. It has traveled 4 meters because it's just moving along the ramp from top to bottom. Okay, so your x here is going to be 4 meters, your acceleration is going to be what you just found in F. So again, we can use that formula C to solve for that, using all the values that we found so far. Part H is what we call path independence. Because we're looking at a frictionless ramp, it shouldn't matter to the speed whether or not it's going down the ramp or being dropped from the same height as the ramp, right? Gravity, a component of it, is making it accelerate regardless. So it ends up going to the same speed regardless of what path it ends up taking. So for this one, it's falling a distance of 2 meters and it's in free fall. So your acceleration is going to be 9.8, still dropping from rest. So you're still going to be using the same formula, but you're going to be using different values. Your initial speed, still 0. Your acceleration on this one in free fall, 9.8. The distance it has fallen is now 2. Okay, you should end up getting the same answer between H and G. If you don't, something happened, talk to me. 3 is the exact same process. It just has different values for the ramp. You've got 4 meters long for your hypotenuse. You've got 1.5 meters high. So that's just going to be switching the values that you plug in to find your angles. Beyond that, you're using the exact same formulas. When you're looking for the normal force, that's just the perpendicular component of your force. Just use FW cosine theta. When you're looking for the parallel, FW sine theta. Acceleration, G sine theta. Final speed, use formula C. Final speed when it's being dropped, use formula C. 3 and 2, basically the same thing, just different angles. All right, so we are done with ramps number 1. Let's look at ramps number 2. We have got a 5 kilogram block sliding down a 30-degree ramp with a coefficient of friction of 0.2. Determine the mass of the block. Well, that was a given piece of information. Mass of the block is 5 kilograms. Look at us go. B, weight of the block. I happen to know this one off the top of my head because I've seen it 5,000 times. Weight of the block is just mass times gravity. All right, so 5 times 9.8. In this case, we end up with a weight of 49 newtons. Perpendicular component of the weight. All right, so as before, FW is just equal to your weight times the cosine of your angle. F perpendicular. Stupid. There we go. Looks like a cactus. A little saguaro. I'm just going to rewrite that. Looks stupid. There we go. F parallel, perpendicular, equals FW cosine theta. Voila. D, normal force. Your normal force is just equal to your perpendicular component. All right, so you're good to go. Just take whatever you got for C. That's your answer for D. E, the friction force. All right, so with the information that we've been given, we were told that our coefficient of friction was 0.2. And we know our normal force. So thinking back to when we were talking about horizontal friction, friction is just your coefficient of friction, that ratio there, the 0.2, times your normal force, what you just found in D. Okay, so if you want to find that friction force, just multiply those two together. All right, F, we're looking for the parallel component of the weight. So just like with all the other ones, when you're looking for the parallel component, that's just going to be your weight times the sine of your angle. Okay. Net force. All right, now with this one, we need to do a little bit of thinking. All right, this thing is sliding down a ramp. Okay, so let's think about the forces that we've got. You've got your weight going down. You've got this force here, your perpendicular component. It's canceling out with your normal force. All right, so those two completely cancel away. So what we're left with is our parallel component and our friction force that we don't know. Or we actually already found our friction force. So net force is the sum of all of our forces. All right, so we've got Fn, we've got F parallel, we've got F parallel, and we've got FF. All right, these two are always going to cancel out. Fn and F perpendicular, just gone. Okay, so the net force here is just our parallel component plus our friction. Here's the rub, though. They're pointing in different directions. All right, they're pointing in exactly opposite directions. Okay, so one of these needs to be negative. And you just add them together. There's your net force. Okay, so just take FF and add it to F parallel. Make one of them negative. You got your Fn. F net, I mean. H, acceleration. F net is equal to mass times acceleration. Okay, you've got your F net. You just found it in part G. Okay, you've got the mass of this thing, 5 kilograms, so just divide that F net you just found in G by 5. There's your acceleration. Hurrah. And hey, look at that. We just drew a vector diagram. So your vector diagram will look like we found in G. Dunzo. Next part. We've got a 5 kilogram block sliding down a 40-degree ramp. The coefficient of friction is 0.25. We're looking for the acceleration. Basically, we've got a coefficient of friction. We've got an angle. We've got a mass. We're looking for acceleration. All the steps that you did, A through H, you're doing them again. It's just not walking you through it. Okay, so you're still going to have to find your parallel component. You're still going to have to find your perpendicular component. You're still going to have to find your friction. Using the exact same formulas that we just used, you've just got different values involved. Instead of 30 degrees, you've got 40 degrees. Instead of 0.2 for your coefficient of friction, you've got 0.25. All right, but the process of finding that acceleration is exactly the same as in number 1. Okay, so look back at what you did in number 1. How did you find each variable? Work your way through. You're looking for that acceleration. To find acceleration, you need net force. To find net force, you need F parallel and FF. So how do you find those two? How did you find them before? Do it again. Okay, so that's number 2. It's basically number 1, but it's not holding your hand through it. All right, so just follow the same steps you just did with new numbers. All right, 3. A 5 kilogram block slides down a 25-degree ramp at a constant speed. That is a very important piece of information. Constant speed, thinking about Newton's first law, means that all of our forces have canceled out. Okay, so going through this. 3A, parallel component. Same deal as usual. Take your weight, multiply times the sine of your angle. Okay, B, perpendicular component. FW times the cosine of your angle. Done. Normal force. Well, that's not a C. That's not even close to a C. C, your normal force, just equal to your perpendicular component. So whatever you found for B, that's your answer for C. Net force. This is where we need to think about the fact that it's going at a constant speed. All right, if your net force is 0, that means that all of your forces have canceled out. All right, whatever force you got down the ramp, it equals the forces going up a ramp. So what's your net force? If it's not accelerating, if it's going at constant speed, your net force, 0. Okay? Wait. Crap, that's F. Solved the wrong thing. F is that. D, your friction force. Oh, okay. All right, so. Wait, what am I? Oh, God, I'm all over the place. Okay, so C is not solving for Fn. D is solving for Fn. So, putting that down there. Jesus. C. Let's think about C. So, we're going at constant speed. Let's think about the forces we've got on this thing. All right, you've got your parallel pointing down, you've got your friction pointing up, you've got your normal pointing off the ramp, you've got your perpendicular pointing the opposite direction of that. All right, these two cancel out. All right, that's how it's not flying off the ramp or flying into the ramp. Okay, so those two just go away. All right, so if you're thinking about your net force, this thing's going at constant speed. Our net force has to be 0, which means that these two forces have to cancel out. All right, so for C, when you're looking for your friction force, because this thing is going at a constant speed, that means your force down the ramp, your parallel component, needs to be equal to your force up the ramp, which is your friction. Okay, so FF is going to be equal to your parallel component. All right, so whatever you got for part A for your parallel component, that is your friction. And we're done with part C. Let's see. So the next part that I didn't do, D was our normal force. We already dealt with that. Coefficient of kinetic friction. Okay, so now looking at part E, coefficient of friction is in this formula. Your FF equals mu times Fn. Okay, your normal force you already found. Your normal force was just whatever your perpendicular component was. Okay, your FF, we already found that. It was just whatever your parallel component was. Okay, so if we're looking for this mu here, you're just going to be dividing Fn over. So take your friction force, divide by your normal force. There's mu. There's your coefficient of friction. Last bit, your net force, we actually already mentioned that. Your net force is just 0 because it's going at constant speed. If something isn't accelerating, net force is 0. All right, so there's number 3. Let's look at number 4. 5 kilogram block accelerates at 1.5 meters per second squared down a 45-degree ramp. Determine the parallel component. Awesome, FW sine theta. Dunzo. Perpendicular component. Awesome, FW cosine theta. Dunzo. Normal force. Normal force is always equal to your perpendicular component, so that'll be equal to whatever you got for B. F net. All right, so looking at our F net here, why do I always do that? So F net, all right, it's not saying it's going to constant speed. Instead, this one's telling us that we're accelerating at 1.5 meters per second squared. Okay, so we're going to think about F net the other way. Instead of as the sum of all of our forces using Newton's second law, F net just equals mass times acceleration. You've got an acceleration of 1.5, you've got a mass of 5, multiply the two together, there you go. Done deal. Friction force. Okay, so we've got all the same forces acting on this thing, all right? But in this one, we've got some net force going down the ramp because it says it's accelerating down the ramp, okay? Which means that this parallel force has to be larger than our friction. We're looking for our friction here, okay? So let's just think about what F net is, all right? It's the sum of all of our forces. You've got your normal force, you've got your perpendicular component, you've got your parallel component, and you've got your friction force, okay? These two cancel out. They're gone. We're looking for FF. We already know F net. We already know F parallel. So if you want to find FF, just subtract F parallel over. There's FF. Done. And then last bit, coefficient of kinetic friction. Again, you're going to be using this FF equals mu times Fn. Okay, so take your friction force that you just found in E and divide by your normal force that you found in B and C. All right, last one on this sheet, number 5. Number 5. Whoo boy. A 10 kilogram object is pulled up a 30-degree ramp with an applied force of 100 newtons. The coefficient of friction is 0.4. All right. AI, we're looking for the parallel component. As with every other time we've found it, FW sine theta. Normal force, as always, it is equal to the perpendicular component, which is FW cosine theta. The friction force is just going to be equal to your coefficient of friction times your normal force. Your coefficient of friction is 0.4. Your normal force you just found in part 2. Your net force. Net force, we need to think about the forces on this thing. So we've got our weight going down. You've got your parallel force that you already found. You've got an applied force up the ramp. You've got your perpendicular component. You've got your normal force. Okay, and last piece of important information is this thing is being pulled up a ramp. Okay, up a ramp means that friction is going to be pointed in the opposite direction. It's going to be pointed down the ramp. All right, so we've got two forces pointing down the ramp there, your parallel force and your friction force. They are pointed the same direction. Okay? Now, when we're looking for our friction there, your F net is equal to the sum of all your forces. Fn, F perpendicular, F parallel, FF, and FA. Okay, those are all the forces that are acting on this thing. But before we start plugging in numbers, we need to think about what direction things are going. These two always cancel out, so we don't need to worry about those. But these are not all pointed the same way. FA pulling up the ramp in the direction of this thing's motion. FF and F parallel are pointed down. Okay? So, these two need to be the same sign. They need to either both be positive or both be negative because they're pointing the same direction. This one, because it's pointed the opposite direction, needs to have the opposite sign. Now, because this thing is being pulled up the ramp, I would probably make this up the ramp positive. Okay, so that means FA, I'm plugging in a positive 100 newtons. Okay, my FA of 100 newtons. All right, for my parallel and my friction, they're both pointed down the ramp. Okay, so even though I ended up with positive values when I was calculating them, they're in the opposite direction. So give them a negative because they're pointed the opposite way. Okay, now when you're looking for your FA, These are both negative, so that means you're adding them to the other side. Sorry, you're not looking for FA. You already got FA. So it's just going to be 100 minus these two forces to find your net force. Okay? And drawing all of that stuff. Hey, look, we already did it. So draw that diagram. Last one. Let's go. All right. So, incline plane, ramp 3. 5 kilogram block sits on a stationary ramp as shown below. It is being held up by a mass on a pulley. The ramp is frictionless. Also, this is a 30-degree angle. Draw a diagram showing all the force vectors acting on the block. 1A. Ba 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 ba. Here we go. We got Fn, we got Fw. As usual, you've got your perpendicular component, you got your parallel component. It says that it's frictionless. There is a force being applied by that thing's weight. This thing pulling down on this pulley is going to be pulling up with an applied force up the ramp. Okay? Voila. Diagram done. All right, calculate the block's weight. All right, so the block's weight is just going to be that 5 kilograms times gravity, mg. So 5 times 9.8, you end up with 49 as the weight of this thing. Normal force on the block, Fn, is just equal to your perpendicular component. So that means it's going to be Fw times the cosine of your angle. D, parallel component, is always going to be Fw sine theta. Done deal. That's a bad theta. Okay. E, determine the net force on the block. It says it's sitting stationary. That's not accelerating. Got an acceleration of 0. Net force is 0. Done. We even got a number on that one. Look at us go. F, determine the weight of the hanging mass. So, thinking about... Oh, crap. Ugh. Turn back on. Come on, man. I'm almost done. There we go. Okay. All right, we're back. Let's finish this off. So, weight of the hanging mass. Weight of the hanging mass is whatever this applied force is. This thing isn't moving, which means that all of our forces have to be canceling out. Okay, so our F net is 0. All these forces are canceling. We've got Fn and F perpendicular. Those two cancel out as usual. So what we're left with is our parallel force and our applied force. If this thing's stationary, that means that the force up the ramp, the weight of this little hanging mass, needs to be equal to that parallel component, which means for F, FA, the thing you're trying to find, is just equal to F parallel. Done. All right. 2, shockingly similar. The only difference is it's got friction. Okay, so this thing is moving up the ramp. All right, so looking at our diagram, still going to have weight, still going to have normal force, still going to have perpendicular component, still going to have parallel component, still going to have an applied force. Difference here, because it's moving up the ramp, you're also going to have a friction force pulling down on the ramp. Okay, so you got 2 forces pulling down the ramp, 1 force pulling up it. For a lot of these calculations here, normal force on the block, hey look, we already got a thing for that. Parallel component, we already got a thing for that. Net force, wait, no, friction on the block. Okay, so friction on the block, we're going to have to use... this is part D. So friction force is just your coefficient of friction times your normal force. Well, we've already got a coefficient of friction. You got 0.25 as our coefficient of friction. You got your normal force from earlier, so just multiply those two together. There you go. We got FF. The weight of the hanging mass. All right. So again, this thing is not accelerating. It's moving up at a constant speed, which means that all of our forces together have to cancel out. Okay. So all of our forces going up the ramp, which would be FA, need to equal all of our forces going down the ramp. So that's our weight, no, that's our parallel component, and our friction force, both of which we have already found. So if you want to find that FA, the force of the hanging mass pulling on this thing, it's just going to be your parallel component plus your friction force, and look at that, you're done. Yay. Hooray, go us. F, looking for the mass of that thing, that's going to be FW equals mass times gravity. You already got the weight of it. It was whatever the applied force was in E. Just going to need to divide by gravity. So divide by 9.8, there's your mass. Hooray, you're done with number 2. Number 3. Going to be very, very similar. Only difference on this one is it is moving down the ramp. So we still got our weight, still got our normal, still got the components of our weight, our perpendicular, and our parallel component still got an applied force that we don't know up the ramp, but because this thing is sliding down the ramp, that now means that our friction force is up the ramp. All right, you've got two forces pointing up the ramp, one force pointing down. Friction will always point in the opposite direction of something's motion. Okay, so let's see. Normal force, we already got a formula for that. We already used it 2 times. Parallel component, already got a formula for that. Already used it 2 times. Friction on the block, already got a formula for that. Already used it once. So that'll just be your mu times the coefficient of friction times your normal force. So that'll be 0.25 times the normal force you already found in part B. The weight of the hanging mass. So, because it is still moving at a constant speed, that means that all of our forces have to be canceling out. So all of our forces pointing up the ramp, which would be our applied force, the thing we're trying to find, and our friction force need to equal all of our forces pointing down the ramp. Well, we already know this one. We're looking for this one. How do we get that over there? It's being added, so just subtract it over. Your applied force is just going to be equal to your parallel component minus your friction force. There you go. There's the weight of the object. Woo! F. Finding the mass of it, we got Fw equals mg. The weight of it is just what you found for Fa in the previous problem. G is 9.8, so divide that over. There's your mass. Hurrah. 4. So close to done. All right, we got a 10 kilogram block, which means that has a weight of 98, because 10 times 9.8, easy peasy. Moving at a constant speed, which means net force is 0, which means all your forces up the ramp need to equal all your forces down the ramp. At a constant speed up a ramp at an angle of 35 degrees, a force of 80 newtons is applied up the ramp on the block. Draw a diagram. Is it moving up the ramp? Diagram is this one. This one. Cool. Determine the coefficient of static friction. Okay, so coefficient of friction is in here. Looking for mu. Okay, so solving that for mu. It's going to be FF over Fn. All right, we can find Fn. Fn is just weight times our cosine of our angle. Cool, so we got a way to find that. Our FF, so thinking about our friction here. Well, we already dealt with that in here. All of our downward forces are equal to all of our upward forces. Basically, Fa, which was 80 newtons, is equal to our parallel component plus our friction. So solving for friction, we're just going to be subtracting F parallel over. Okay, so FF is going to be F parallel minus Fa. And F parallel is just mg sine theta. So, working our way through, do we know mass? Yeah. Do we know gravity? Yeah. Do we know our angle? Yeah, so we can find that. Okay, if we know that and we know that, that means we can find that. If we know that and we can find that, it means we can find our mu. Okay, so you're going to have to work this backwards. Find your F parallel, subtract Fa from it, there's your FF. Find Fn, take FF, divide by Fn. There you go, you're done. Woo! What was that? What's the time? 28 minutes. Hot damn. That's not bad for 3 assignments. Look at me go. Anywho, if you're having any issues with any of the actual plugging things in or identifying any of the variables, you got an outline, but if you need any additional help, feel free to ask in class, before school, after school, during class, during lunch, whenever you want, through email. I don't know, you do you. Just if you're having trouble, let me know. We'll handle it. See you around. Bye.